Hi friends, here I am going to present session 2 of the paper 7 analysis 2 and algebra 4 of 6th semester mathematics. The topic is Euler's formula. So let us we know how Euler's formula comes, how we can derive Euler's formula, what is Euler's formula and its application. Let us see how we can write Euler's formula, how it comes. So we know that by Taylor's expansion, sin theta is equal to theta by 1 factorial minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial minus plus etc. Similarly, the Taylor's expansion of cos theta is equal to 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial minus plus etc. And also the expansion of e to the power I theta e to the power x, that is 1 plus I theta by 1 factorial plus I theta whole square by 2 factorial plus I theta whole cube by 3 factorial plus etc. So here in this e to the power I theta we have I theta whole square, that is minus theta square, I theta whole cube minus I into theta cube, I to the power whole to the power 5, that is plus I into theta to the power 5. So you have to regroup, you have to rearrange the even terms and odd terms, real parts and imaginary parts. We get e to the power I theta is equal to 1 minus theta square by 2 factorial plus theta to the power 4 factorial minus plus etc. plus I into theta by 1 factorial minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial minus plus etc. So the first part is cos theta and the second part is sin theta. So we write e power I theta is equal to cos theta plus I sin theta, so which is called Euler's formula. We can write this Euler's formula in complex number, that is z is equal to x plus I y is equal to r into cos theta plus I sin theta. So this cos theta plus I sin theta is e to the power I theta. We can write complex number using Euler's formula, that is z is equal to r into e to the power I theta. Next, by using this formula we can see some properties and also we can solve some problems. So the first property is argument of z1 z2 is equal to argument of z1 plus z2. So what is argument of z1? It is the amplitude. So if z1 is equal to r1 e to the power I theta 1, the amplitude of z1 is theta 1. If z2 is equal to r2 e to the power I theta 2, the amplitude or argument of z2 is theta 2. So z1 into z2 is r1 r2 e to the power I theta 1 plus theta 2, I into theta 1 plus theta 2. So there the argument of z1 plus z1 z2 is theta 1 plus theta 2. So theta 1 is argument of z1 plus theta 2 is argument of z2. So we get argument of z1 z2 is argument of z1 plus z2. So this is a simple property, one can easily prove this. Similarly, we can prove that argument of z1 by z2, same argument z1 by z2 is r1 by r2 e to the power I into theta 1 minus theta 2. So argument of z1 by z2 is theta 1 minus theta 2. So theta 1 is argument of z1 and minus theta 2 is argument of z2. So we can verify these two properties using Euler's formula. Now we have to solve some problems on Euler's formula. Complex, you have to solve from problems on complex numbers using Euler's formula. So here the first example is if z is equal to x plus I y, how to find real part and imaginary parts of exponential of z square. To find real and imaginary parts, we have to express the given problem in the form of x plus I y. So take z is equal to x plus I y. In all the problems, the z represents x plus I y. So z square is equal to x plus I y whole square, that is equal to x square minus y square plus I into 2xy. So it comes by a plus b whole square formula, a square plus b square plus 2ab. Here I square is minus 1, so it is minus y square. Now exponential of z square is equal to e to the power x square minus y square. We have to substitute z square, e to the power x square minus y square plus 2i xy. Again by using law of indices we can write e to the power x square minus y square into e to the power I into 2xy. Here we can apply Euler's formula. So by using Euler's formula, e to the power I 2xy is equal to cos 2xy plus I sin 2xy. Okay. So here we can say that the real part is e to the power x square minus y square into cos 2xy, and the imaginary part is e to the power x square minus y square into sin 2xy. Let us see one more example. So example 2, find the real and imaginary parts of exponential of 5 plus I pi by 2. So here also we cannot say directly because it is not in the form of x plus iy. So we have to reduce into the complex form x plus iy or into cos theta plus I sin theta. So you can write exponential of 5 plus I pi by 2 is equal to e to the power 5 into e to the power I pi by 2. So e to the power I pi by 2, by using Euler's formula we can write cos pi by 2 plus I sin pi by 2. Here cos pi by 2 is cos 90 degree 0, sin 90 degree 1. So the real part is e to the power 5 into 0 0, and the imaginary part is e to the power 5 into 1, that is e to the power 5. Let us see one more example, that is find the real and imaginary parts of exponential of 1 plus I pi by 3. So here exponential of 1 plus I pi by 3 can be written as e to the power 1 into e to the power I pi by 3. Again using Euler's formula we can write e to the power I pi by 3 as cos pi by 3 plus I sin pi by 3. So cos 60 degree it is 1 by 2, sin 60 degree root 3 by 2. Therefore the real part is e into 1 by 2 and the imaginary part is e into root 3 by 2. Similarly, we can solve the example 4th. So exponential of 3 minus I pi. Exponential of 3 minus I pi is equal to e cube into e to the power minus I pi. So again applying Euler's formula, we write cos pi minus I sin pi. E to the power I theta is cos theta plus I sin theta. E to the power minus I theta is cos theta minus I sin theta, because sin of minus theta is minus sin theta. So sin pi is minus 1, cos pi cos 180 0. So we get real part is minus e cube and imaginary part is 0. So this is about Euler's formula and its application. Thank you.